rather unpleasant to try and work out. The relative biological effectiveness, so the radiation weighting factors are selected to represent the relative biological effectiveness of different types of radiation in producing stochastic effects. So stochastic effects, we'll cover those in later lectures, but basically that's stochastic effect is a random effect. So it might be, for example, the induction of cancer later on, so that's considered a stochastic effect. But we'll cover that in later lectures. The relative biological effectiveness of one radiation compared to another is the inverse of the ratio of absorbed doses causing the same biological endpoint. So if you want to do the same amount of damage to a cell, or to, say, two identical cells with different types of radiation, how much do you have to increase one type of the dose from one type of radiation to cause the same effect as the other? So this brings us to the equivalent dose. So we know now that the absorbed dose from two different types of radiation aren't equivalent. It depends on the type of radiation. So this brings us to what's called the equivalent dose. It's given by H, and that is simply the radiation weighting factor multiplied by the absorbed dose. If you've got a radiation field of multiple types of radiation, so for example from an alpha emitter which emits alphas and gammas, then you have to sum up the relative contribution from each type of radiation. So each type of radiation is going to have its own absorbed dose and its own radiation weighting factor. So there's some examples of this, some exercises for you to do on in your tutorial questions, available near the lecture slides. You'll see that it's a fairly simple sort of calculation. It shouldn't be difficult for you guys at all. The equivalent unit, or the unit for equivalent dose, I should say, is the sievert. All right. So the sievert is the same basic unit as absorbed dose, so it's energy deposited per unit mass, but there's a name change to emphasise that it's not purely a physical quantity, it's more of a biological response. As I said before, if you have a mixed radiation field of different types of radiation, you need to sum up the effects from the different types of radiation. An exception is the case of Auger electrons emitted from the nuclide bound to DNA, and that's treated separately, and we're not going to get into that in this unit. Now, to complicate things a bit more, there's a variation in response of different tissues to radiation. So, for example, the gonads are more sensitive than the skin, so we now have to apply a tissue weighting factor, which is given by WT, to the equivalent dose. So you apply this to the equivalent dose, not the absorbed dose, and that will give us the what's called the effective dose, given by the letter E. So the effective dose is the equivalent dose on multiplied by the weighting factor for the tissue that the equivalent dose is incident on. And then if you have multiple tissues, you have to sum up the different tissues. The unit for effective dose is also the joules per kilogram, and it's also the sievert, which can be confusing. So the tissue weighting factor represents a relative contribution of a particular organ or tissue to the total detriment of the organism, so the person, resulting from a uniform radiation in the whole body. So if you irradiate the whole body, what's the contribution of each different organ to the total detriment of the body? But sometimes you don't irradiate the whole body. So for example, in medical situations, so medical imaging and radiotherapy, you're only irradiating a few tissues. And so Tissue weighting factors can vary with the population of exposed individuals. So different populations have different weightings. So some people are more sensitive than others. And so there's a considerable section of the ICRP recommendations to deal with the relative risks to different populations. But given if you don't know the relative risks of the different populations, there's a set of weighting factors that can generally be used. So here's the tissue weighting factors, the 1990 recommendations and the 2007. We will be using the 1990 ones, just simply because, well, the table's better, to be honest. When you go out into work, in practice, you would use the 2007, but just for the simplicity's sake, we're going to stick with the 1990. Hopefully, you guys, if you need to apply this in a real situation, you will need to use the right tissue weighting factors. So it's desirable that the uniform equivalent dose over the whole body should be numerically the same as the effective dose. All right, so the equivalent dose and the effective dose should be the same over the whole body. So this is achieved by, if you add all of these up and all of these up, it should add up to 1. So if you have a whole body irradiation, the effective dose should equal the equivalent dose. And the time that it's different is if you don't irradiate the whole body. So the tissue weighting factors should be independent of the type of energy of the radiation. So this is an approximation, and it's an assumption, and it may prove to be wrong in the future. But that's what we were sticking with for the time being. Now, effective dose and equivalent dose, like as before, there are exercises on Blackboard for you guys to go through. Now, the final thing we're going to look at is committed effective dose and committed equivalent dose. So far we've assumed that, whoops, my pen's not working. We've assumed that the doses we receive are external radiation exposure, but you can actually have internal radiation exposure. So this might come from, for example, a miner might breathe in, so a uranium miner might breathe in some uranium dust, and that might stick to their lungs and stay in their lungs for the rest of their life and continue to irradiate them from within for the rest of their lives, and they can't get rid of that. So external exposure ceases when the source is turned off, but internal exposure doesn't cease, so they're always committed to receiving that dose. So this is going to apply, for example, when you're working out the dose limit that a particular worker is allowed to receive, and we'll be doing this in later lectures. If, for example, they're already receiving some internal dose from some lodged radionuclide, then you have to reduce the dose limit for that worker to allow for the fact that they're already receiving that dose. So we introduced the term committed equivalent dose and committed effective dose. And the committed equivalent dose is just the equivalent dose with the symbols just got a little tau, and likewise for the effective dose. So this is given by the annual dose integrated over the lifetime of the person. So for adults, the lifetime is taken to be 50 years, for children 70 years, because children are expected to live longer, and it's integrated. So what this means is for long-lived radionuclides, say for example uranium, which is most isotopes of uranium have very long half-lives, so this will virtually not change over 50 years. But if you have a shorter-lived radionuclide, say cesium-137, which has got a half-life of 30 years, so over the 50 years it's going to actually change. So this interval becomes more important to calculate. So that could complicate things a little bit more. The committed effective dose is you have to allow for the different weighting factors as well for different tissues and different radiation types. So the committed dose, there's some exercises or tutorial questions for you to go through. They're not too difficult, but if you have any questions, you can ask me. And that's all for this lecture. Remember, I'm available to answer questions, and please don't forget the online test. It's worth marks to you. All right, thank you.